Welcome back, Earth Scientist, and let's take a look at this picture of Bryce Canyon National Park. I took this on our very first geology field course in a very large storm event. We had been traveling during monsoon season, and usually Utah and Arizona are pretty dry except for the months of July and early August, and that's exactly when this was. So why would a big cloud system like that start to develop? How does it happen? What kind of air pressure is involved, and how can you determine when storms are coming? Simply by knowing a little bit about air pressure. All right, what is air pressure? That should be the first question we ask. It's the amount of force or weight that is actually pushed from the air above us down onto the surface. The weight of air at sea level is 14.7 pounds per square inch. That decreases with increasing altitude. So the higher you go up in altitude, the less the air mass will weigh. We measure all air masses in terms of millibars. And millibars are just a unit of measurement for the weight of an air mass. And standard sea level pressure in millibars is 1013.2. That's a guaranteed test question, 1013.2. Now, the inches of mercury at standard sea level, if you were to look at that in mercury, is 29.92 inches of mercury. We use that with a barometer, and a mercury barometer has been around since the 1600s, and it's simply a tube filled with mercury that measures temperature, probably much like you used as a child to take your temperature if you had a fever or not, except this takes the air pressure measurement on Earth. Barometers, an aneroid barometer is one that's used without liquid, and it uses an expanding chamber to assess the amount of air that needs to be, or that's currently in an air mass, to inflate and deflate that particular chamber. And it puts a bar graph together, or a barograph, that shows a continuous reading of air pressure. There are basically two ways that we can measure wind. And wind is associated with unequal heating of the atmosphere. We look at direction and speed. Now, when you hear about, okay, there are northwesterly winds today, what does that mean? It means that the winds came from the north and they blow from the north towards the south. So winds are directly labeled from the direction in which they originate, not the direction that they are headed. We can use a couple of things to help us make wind measurements. We can look at compass points at a scale of 0 degrees to 360 degrees, and we can determine some winds always come pretty much from the same direction. They're called prevailing winds. Speed is measured with the cup anemometer, which is way up here in this thing, right up in this section, and we can determine the speed and the direction simply by this type of a tool. You'll usually see one of these things at an airport. Now, a weather map shows how winds are developed and also shows you specifically the amount of millibars in terms of something called isobars. If you've ever seen a topographic map, it uses feet to separate the contour intervals. Well, this is much the same thing, but it's looking at air pressure instead of elevation. So horizontal movement of air comes out of areas of high pressure into areas of low pressure. So you'd have a high pressure system here moving into a low pressure system here. What controls the wind that does that? Well, it's a pressure of gradient force. Isobars simply represent the lines of equal air pressure. That'll be a test question. So this line of 1012 is all the same, and that's why it's in that line. Everything in between is something else, but this line at 1008, all of this would be 1008. Coriolis effect does have an impact on wind. Apparent deflection in wind direction due to Earth's rotation occurs, and it moves to the right in the northern hemisphere and to the left in the southern hemisphere. One other factor that affects wind is friction on the ground. Friction acts to slow the movement of air as it comes in contact with the ground and slows it down a bit. What are some forces that affect wind? Upper air winds generally blow parallel to isobars, and they are called geostrophic winds. The jet stream is a big giant river of air, and that's a high altitude wind pattern that moves at a very, very high fast speed, which is literally 120 to 240 kilometers per hour. Now there's other things that you need to know about pressure systems. There's high and low pressure systems. A cyclone is a low pressure system. So the pressure decreases towards the center. In the northern hemisphere, they're going to be rotating in a counterclockwise, and they're going to be moving towards the inwards in a convergence pattern. In the southern hemisphere, they're still converging in the intersection, but they're moving in a clockwise manner. Cyclones you should associate with poor, rainy, bad weather. So low pressure equals rainy weather like clouds, precipitation, thunderstorms. An anticyclone would be just the opposite. It'd be a big H on the map. So a high pressure system would be considered an anticyclone, and a low pressure system would be considered a cyclone. On anticyclones, winds that happen with these things in the northern hemisphere, they tend to be outward and diverge in a clockwise manner, and in a southern hemisphere, anticyclones move in a divergent manner outward, but in a counterclockwise fashion. Anticyclones should always be associated with high and fair weather conditions. So here's an H that would be a anticyclone. The L would be a cyclone. One other thing I might point out, take a look at the millibar readings and notice how much higher they are over here than here. You're like, well, they're only a difference of 10 or 11 or 12 millibars. That's substantial in weather. So weather can be dictated by just a handful of changes, a slight difference in millibar readings. Airflow associated with surface cyclones and anticyclones, remember one's divergent, one's convergent. When you have the air coming down, it's going to be in an anticyclonic fashion. It's going to be converging aloft and coming downwards in this section, and there's be surface divergence. And the airflow is going upward when you have a cyclonic flow, and it's pushing that air up, causing a low air pressure system here, and so you get surface convergence. And here you should see bad weather. This area you should see high and good weather. The reason it's going to be good weather, this big H right here, is going to push down on the earth and kind of prevent any unequal heating of the atmosphere. So when you look at the time of day and air pressure, notice that there is interesting, when you look at the land and the water, you can see during the day, if you get cool water and warm land, you're going to have very similar conditions than you would at night, where you have warm water and cool land. It's a very intriguing idea. It's almost identical. It is identical all the way up the board. So atmospheric circulation of air masses is caused by unequal surface heating, and that generates winds. On the rotating Earth, there are 3 pairs of atmospheric cells that redistribute heat across the globe. So let's find out what they are. Subtropical high pressure zones exist between right at the 30 degrees north and south latitudes, and these are the locations of our massive deserts around the world. So the air traveling equatorward from the subtropical high produces the trade winds, and this air traveling poleward from the subtropical high produces the westerly winds. Subpolar low pressure zones are warm and cool winds interact in this location, and the polar fronts will actually generate here and create areas of storms. There's also a polar high pressure zone, which is a cold subsiding air where the air spreads out on an equator ward. There's also a polar high pressure zone where air spreads equatorward and produces polar easterly winds, and polar easterlies collide with the westerlies along polar fronts for some interesting weather. So this air is going to be coming from the section up here at the poles and working its way down. Convection currents move that material around, and basically you get a big gigantic conveyor belt of movement of air. So that puts together our global circulation of winds that we learned or will be seeing in another lecture. So you have your polar high here, your subpolar low here, then you get your polar fronts that come in and create your westerlies where the trade winds and the subtropical highs meet, and then you're going to have a low pressure system right in here where you have your equatorial lows. So let's look at those and put them on degrees. your equatorial lows, and your polar highs. So this should be a high pressure system, low pressure area. Then you can see it alternates from low to high, low to high. That's really easy. So on your test, I may ask you, have a diagram like this and say, which one am I looking at? Subpolar low, subtropical high, equatorial low. So the wind patterns are deflected based on Coriolis, and they alternate. So let's just kind of show that to you. You can see that they are deflecting. They start off at the poles, and they're deflected in a counterclockwise manner in the northern hemisphere. And then they're going to be, Coriolis will move them to the right here, to the left, and so forth. So now you're looking at where the winds are being produced, and the northeast and southeast trade winds are made right here because of the equatorial lows connect to these subtropical highs, and then the westerlies are where the subtropical highs connect to the subpolar lows. They're your polar easterlies on both sides. So influences that could affect general atmospheric circulation, continents can play a role in that. Seasonal temperature differences disrupt the global pressure patterns and the global wind patterns. That can be a seasonal effect. Influence is most obvious in the northern hemisphere, especially during monsoon season when you have a change in wind direction. So when you're looking at pressure across the globe, and we're going to look at associated winds for January, I want you to see where it has some of the lowest readings on the map. And I really want you to focus in the Atlantic area, and you'll see it with a very, very clearly where that might be located. And then you'll see way down here that you get some similar numbers down here as well. And I want you to check out the latitudes for that and kind of figure out where we are. So here's right about 60-ish, and here's the Icelandic low, and down here is 60 degrees south. Are you seeing a pattern there? So pressure matters by where you are on the Earth, because each one of those blocks of high and low pressure system is a global band that goes around the globe. So ocean currents help move and distribute the heat that's in the ocean, and the wind patterns actually play a role in that. So winds actually do impact how we move that water and how currents are developed. So what is a monsoon season? A monsoon is where you get an atmospheric circulation that happens during warm months, and the air flows onto land. If you get very warm, moist water that comes from the ocean and produces a very rainy season. Places that get that in North America would be places like Mexico, Arizona, Utah, parts of New Mexico, Colorado, what we would call the Colorado Plateau. During the winter months, these areas, you have air that flows off the land that's very dry, and you tend to have very dry weather. You don't tend to have massive amounts of rain. Matter of fact, you'll have virtually none. Most of these areas are desert-like. In January, high pressure over the land produces the dry winds because the air is flowing into a tropical convergence zone. And so you're going to get very dry weather. These high millibar readings should be indicators of that because it'll produce high weather systems. In July, the opposite would be true, where you're going to get a very low pressure system on land causing winds to flow off the ocean that are very warm and moist and bring in some low pressure systems. Thus, you would have monsoon season. In the mid-latitudes, this is the zone of where we create the westerlies. It's a very complex set of air conditions, and the airflow never stays the same because it's constantly interrupted by storm systems known as cyclones. Cells tend to move from west to east in the northern hemisphere, and they create two types of patterns, an anticyclonic and then a cyclonic type of flow. The paths of these storm systems or high weather systems are associated with the upper level airflow, which dictate which one you're going to have. Something called a Rossby wave occurs where you can get actually pairs of these types of weather patterns. And you can see here's a cold polar air. It's beginning to sink right here, coming in contact with that low pressure system here. And it produces a little arm on both sides. Well, these little pools or cells of material are referred to as Rossby waves. And these develop at polar fronts and form very interesting convoluted waves that pinch off, making areas of low pressure and substantial stormy type of conditions. Another thing to consider is sea breezes and land breezes and how they impact wind patterns. When you have a sea breeze blows cool water onto warm land, and that causes unequal heating. And notice that you'll get your low pressure system on land right here, and as that air rises, it becomes a high pressure, comes back over to the water, low, comes back down to the water down here during the day and makes a high. The opposite rotation would happen during the nighttime, where when that warm water blows onto land, you get a high because the land is cooler, producing a cooler energy, comes low up here, and then reverses its order. It actually comes and goes this direction, actually. So they operate in opposite directions, whether it's day or night. So this one goes in a counterclockwise, this one goes in a clockwise manner. Valley breezes and mountain breezes are different. By the way, the definition of a mountain versus a valley is different. A mountain must have at least 900 vertical feet of elevation from the surrounding flatlands. So you get a valley breeze that comes through, let's say, Yosemite Valley, and picks up this warm air and pulls it off, and you get the heat coming off of the mountains during the day. During at night, that's going to drive, that cold air is going to come down the sides of these mountains and come down through the valley, producing a nice cold breeze. So there's a phenomenon called El Niño and La Niña. These are very similar but extremely different. El Niño is a countercurrent that flows southward along the coast of Ecuador and Peru in South America, and it's known to have unusually seasonably warm waters around Christmas time, where you get blocks of upwelled of colder, nutrient-enriched water. And this is so nutrient-enriched that the fish that require that nutrient resource around that area, which happen to be anchovies, starve to death from lack of food. You're like, well, too bad for them, because if you're not an anchovy lover, then you're probably happy about El Niño. From a weather perspective, we're not so happy for humans. Let's talk about why. We've had a couple of really bad El Niño events over the last 3 decades, and one that's probably the most notorious occurred in 1997 and 1998, where heavy rains in Ecuador and Peru occurred. Catastrophic rainy weather, mudslides, and so forth occurred in California. And then we saw atmospheric circulation changes on a global level. Pressure change between eastern and western Pacific, called the Southern Oscillation, which is what El Niño is. This changed the trade winds and created a major change in the equatorial current system in the ocean. So when this did, the warm water flowed eastward and changed weather patterns around the globe. So this typically happens in a systematic amount of years, and now we can recognize El Niño and La Niña and plan for it. When you compare normal years of flowing of high cold water pressure, and then you can see that this pressure turns and makes a low and comes back around. What's going to happen during an El Niño year is you're going to get, instead of having cooler waters, you're going to get unseasonably warmer waters off the coast of South America, which throws off the equatorial currents all the way around. Here's what happens. You can see this warmer water starts to move out this way and can create literally global problems all the way throughout the Pacific Ocean basin. So the opposite would be true in La Niña. You would get some cold water out here that's unseasonably cool, causing an opposite effect. In a normal year, low pressure dominates parts of Malaysia and Australia and New Zealand area. And in an El Niño year, low pressure moves east to central part of the Western Pacific, causing more problems in this region than you would normally had seen during a normal year up here. So you can see that's right along the coastline of California, and that wreaks havoc on an extremely populated area. El Niño and La Niña, like I said, are similar. Here's how La Niña is different. It's triggered by colder than average surface temperatures in the eastern Pacific. And a typical La Niña winter blows colder than normal air across the Pacific Northwest and Great Plains while warming much of the rest of the United States. So this area could experience high amounts of blizzards during that winter, creating extremely cold winter conditions. Overall, global rainfall patterns are dictated by the process of how wind moves from and across the globe. All of that's directly correlated to ocean currents. I'm hoping you're beginning to see that all of this is connected. Our science isn't just four disciplines of science, they are all interrelated. So when you look at the areas that have the highest concentrations of rain, notice their latitudes. They're usually somewhere within the Tropic of Cancer and Tropic of Capricorn, minus one area that's in a temperate rainforest up here. And you can begin to see that these areas have high populations of people. And I'm going to look at this section being the second most populated section of the world, China being the most populated. And then you get parts of the United States all have a considerable amount of population around the coastlines in these sections right here. Every rainfall just doesn't happen by accident. There's a direct correlation to which wind belt that you're in, the pressure that's in each one of those wind belts, and how the land is laid out in terms of, are you going to have mountain breezes, sea breezes, valley breezes? What kind of wind patterns are you going to have? And are you going to have cyclonic or anticyclonic storm events? It's very complex. So when you're thinking about meteorology, it is not a simple science. This is a very complex science with complex modeling that must occur in order to help predict weather in a way that can service humans to make better plans for safety. See you at the next lecture. Bye.